All right, so we started with principles of network applications. Now we continue with web and the HTTP. First, a quick review. Web page consists of objects, each of which can be stored on different web servers. By objects, we mean, JPEG images, maybe Java applications or CSS files and so on. Anything included in an HTML, actually, web page is referred to as object. The HTML file itself is also an object here for us, okay? And good thing is that you can store them on different web servers. Objects can be HTML file, JPEG image, Java applet, audio file, and so on. Web page consists of base HTML file, which includes several referenced objects, each addressable by a URL. For example, here we have the, someschool.edu. This is the host name. After this slash, actually, by this you actually reach to the server that provides this service. This path name actually refers to most probably a folder and file on the server. So you can directly refer to an image. Of course, if that image is publicly available to outside, depends on your server configurations. This way you can request. So this is a URL, okay? Very important for us, but I think everybody is familiar with this. So let's look at HTTP overview. So this is Hypertext Transfer Protocol, Web Applications Layer Protocol, Client-Server Model. At the client side, we have browsers that implement this protocol, right? So a browser that requests, receives using HTTP protocol, and displays web objects. And at this displays, actually the RFC doesn't explain how you to display it. So this is why some web pages might look a little bit different when you visit that web page with different browsers, okay? So this is why sometimes you have to check, especially if you do some graphical design, tables, and so maybe something will overflow in another browser. At the server side, now web server sends using HTTP protocol objects in response to requests. So at the client side, you use browsers, but at the server side, you use a server application, most probably Apache. More than 50% of the world actually uses as the server. So it would be nice if you would be familiar with Apache server actually. So in the picture, it is also Apache web server. So you can also request it from your PC, but you can also request it from your mobile phone, right? So here you have Safari browser, you have Firefox browser, but still it works because we, design the application so that it will work on different operating systems and different applications. HTTP uses TCP, as you might guess, because we want reliability here. Client initiates TCP connection, so it creates a socket to server, port 80. Server accepts TCP connection from client. HTTP messages, application layer protocol messages, exchange between browser, HTTP client, and web server, HTTP server. Then the TCP connection is closed. So let's look at this in a minute with pictures. So here, as you can see, HTTP is stateless. Server maintains no information about past client requests. Protocols that maintain state are complex because past history state must be maintained. If server client crashes, their views of state may be inconsistent, must be reconciled, and so on. Okay. For this reason, we will talk about cookies in a minute. But let's see persistent and non-persistent HTTP first. So HTTP connections has two types. So you actually, okay, let me explain what they are, and then I will explain how you can choose it. So in the non-persistent HTTP, TCP connection is opened by the handshake, we will mention in a minute. At most one object sent over TCP connection, for instance, the HTML file, and TCP connection is closed. But in the HTML file, you will realize that there are some JPEG images. So you will repeat this process again and again to download all of those objects. So downloading multiple objects require multiple connections. In the persistent HTTP, TCP connection open to a server, multiple objects can be sent over single TCP connection between client and that server. TCP connection is closed. So the TCP connection is remain open until you request all of this data. But maybe there is an attack and you want to create a TCP connection and do not want to close it. So there's a timeout actually at the server side that you can configure yourself. So keeping it too long might cause denial of service attacks to become easier. So let's look at the non-persistent HTTP example. In this example, we visit a web page. So this is probably home.index and there is an HTML file there, but it also contains 10 JPEG images. So what you do is as follows. You create a TCP connection and the server accepts this connection, notifying the client. All of this happening at port 80. Now you send your request, which is this. Okay. Initially, you don't send it. You just send a classic hello image message, which is TCP handshake part. Now you send your request, this URL. So they send you the HTML file. Okay. HTTP server closes the TCP connection, and client receives the response containing the HTML file. Displays this HTML on your browser, but now realize that there are 10 reference JPEG images. So you have to repeat all of these steps 10 more times. Okay, this is the bad thing about non-persistent. So we try to measure it with response time, RTT, to show that it takes longer time to download a web page if you use non-persistent connection. Okay, so RTT defined is as follows: time for a small packet to travel from client to server and back. So you create the TCP connection, server replies back. This is 1 RTT because your reply is returned to you. Okay, now you request the file, you receive it. If the file is small, this is just 2 RTTs. But if file is somewhat large, you also wait to download the file. So it takes at least 2 RTTs plus downloading the time required to download this file. So HTTP response time per object is 1 RTT to initiate TCP connection, 1 RTT for HTTP request and first few bytes of the HTTP response of the return, then the object file transmission time. So it is 2 RTTs plus file transmission time. But in the persistent, which actually become available with the version HTTP 1.1, so if you use HTTP 1.0, it is always non-persistent. In HTTP 1.1 and the later ones supports this. So in your browser settings, you might choose if you want to do it in a persistent or non-persistent way. And also there is the configuration at the server side. Maybe you request non-persistent communication, but server doesn't allow you to do it. Okay, so it depends on the configuration of both sides. So it requires 2 RTTs per object, which is we want it to be 1. Operating system overhead for each TCP connection, because each time you create an socket and so on. Browser often open multiple parallel TCP connections to fetch reference objects in parallel, because now you realize that you need to download 10 JPEG images, right? Instead of creating 10 TCP connections in a serial way, you can create 10 TCP connections in parallel and request different JPEG images at the same time. So this will cause a huge load on the server because they have to create TCP connections many times. So to overcome this problem, we have persistent HTTP. Server leaves connection open after sending response. Subsequent HTTP messages between the same client and server sent over open connection. Client sends request as soon as it encounters a reference object, as little as 1 RTT for all the reference objects, cutting response time in half. This is the idea. So HTTP request messages can be in 2 types, request or response. HTTP request message is ASCII, human readable format, is something like this. So it is like get, then the URL and the version you are using. Okay, this is the request line. Header lines are as follows. Here you are providing, which host you are communicating to, your browser version, and so on, which language you are using. Because here you are saying accept language, and because if on the web server, if the object is available in multiple languages, they will try to send you the English one. Okay, this is the header lines. So in the general format, this is actually, what RFCs explain at the end. So here you have the method, URL, version, header field name value. So you can have a lot of headers. So of course you have to define host, but accept language or accept encoding are just optional headers. You don't have to have them, all of them. Yeah. Connection here, it says keep alive, saying that this should be persistent HTTP. If you want non-persistent, then you should write close here instead of keep alive. Okay. Right. So when you request something, you have the header files. Actually, you don't have the body most of the time, but in the return response, you would have the object you required as the entity body here. Okay. So you have different types of request messages, post and get. If you're familiar with PHP or Perl programming, you will notice that when you create a form, you use this command. So let's look at the difference. Post method is that web page often includes form inputs. User inputs sent from client to server in entity body of HTTP post request message. So if you go back, you fill the form and send your request message, but also put your form data here, the fields you filled is included here. In the get method, you don't write it here, but you put it at the URL site. Because, for instance, if you fill a form and you are going to search for monkeys and bananas, let's say, so these are the two inputs you filled in the form. Instead of sending as the post method, if you send it as the get method, you would include this data from the user to the end of your URL. Okay. This is also important because in the past, people put passwords and usernames here. Okay, I said past, but you should be familiar that a few months ago, TÜBİTAK sent me a survey. I've started to filling it, and in the middle of it, I said that, okay, I will continue later. So there was a button, save and continue later. So I saved it. When I click the save button, it asked me to write my email address and choose a password so that in the future I can come back using the same email address and the password. Okay, so I felt that something is tricky, so I gave a very fake password, nothing I use someplace else. So I received an email saying that my survey is saved, so I can continue it any time later. So here's the link to continue it later. But that link actually contained my email address, my name, and my password at the URL. And when I contacted them, they were very surprised. But they corrected it in just a few days. But if I didn't notice it, they wouldn't correct it. And if I use their password that is the same as my Gmail address, then I will lose my Gmail account. That's an instance. Okay, so get method is tricky. So this is why you need to know how these things work. Okay, because you might think that, okay, we are using TLS, so everything is encrypted, but your URL is actually sending it at the public, so everybody sees it. Okay, there are two other methods that are not much heard or used. Head method is as follows: request headers only. That would be returned if specified URL were requested with an HTTP GET method. So let me explain it in this way. Here, okay, I request an HTML files with a GET method. So they send me, I think here, the HTML file, right? Instead of GET, if you are only requested with the head command, they will send me the headers, but not the file itself. So you might think that, why would I do that? Actually, most of the time it is used for debugging. Okay. Put method uploads new file to the server, completely replace file that exists at specified URL with content in entity body of post HTTP request message. Of course, this gives a some power to the user who can use the put method. So you should only allow it in a proper times. For instance, maybe somebody wants to update their profile picture, so you can use put method, but you should be sure that they will not be allowed to modify other files and so on. So let's look at the HTTP response message. Here, as you can see, you have the HTTP version. 200 OK means that okay, you requested an object, we have that object. So this is, otherwise, if there weren't here, you will see like 400 or 4 and so on. So this is the headers, and this is the data that requested. So if you requested it with get method, then you will obtain all of them. But if you requested it with head, the server would only send you this part and not the remaining part, the data. So this speeds up the things when you use, when you want to do debugging. Okay, here are some famous codes. 200 is OK. 301 moved permanently. Requested object moved, new location specified later in this message. So browser sees it and asks you if you should follow the new path and so on. 400 is bad request, not understood by the server. 404, very famous one, requested document not found on the server, but you have to be careful about it here, because maybe the file is there, but your internet service provider didn't want to provide it to you. So when you see 404, this doesn't mean that the file is not there. Sometimes it is there, but you are not allowed to see it. Okay, one way to check it as well. Actually, this works two ways, because in a Brazilian web page, I received 404s for a long time. Then I realized that I can visit that web page when I'm abroad. So that web page works when I'm in Germany, but not in Turkey. So I thought that my internet service provider somehow blocked it. So this is generally what happens. But for that scenario, it wasn't the case of my ISP, but it was the hosting servers in the Brazil. Because in Brazil, they received a lot of hacking attempts from Turkish IPs, so they blocked the web page to Turkey. And you could never know that without asking them, right? So a good way of checking is that, use a VPN and see if it works, or a proxy if that object is there. Yeah, 5.5 is HTTP version not supported. Not everybody is updating their server, or sometimes maybe they don't want to support older versions like HTTP 1.0 and so on. So there are some methods to do this connection. Netcat is an example. It is important to do it by hand. You can also use Telnet, but most of the servers no longer support Telnet due to security problems. But you can simply on the command line try to connect to a web page, then write your get command and look at the response. Of course, Wireshark can be looked at to capture what's sent, and we will use them in our exercise. Yes, important topic, cookies. So we said that the HTTP is originally stateless, because you request something, maybe 5 days later you visit the same web page, and maybe the web page didn't store anything, so they don't know who you are. And this is actually what we most of the time want, because we want to have some privacy. We want to surf the web anonymously and so on. But cookies actually is a state that has a state, but it also creates a very privacy concerns, which I will try to explain in a minute. So let's first see how it works. So no notion of multi-step exchanges of HTTP messages to complete a web transaction. So in a stateful protocol should work like this. Client makes 2 changes to X or none at all. So at the server, there is a value X. So you lock data record X. They say that, okay. Now you tell them to update it. They update it, and so on and so forth. So because they know who you are, and you are allowed to change, okay, in a stateful protocol. So at the middle of it, if the network connection or client crashes, you will have different versions of the data. So you have to somehow mesh them. Actually, this kind of thing happens in Dropbox, right? You have different computers. In one of them, you change it, but sometimes during the upload, there is a problem. So Dropbox actually creates two versions of the file and asks you to choose one. Also, in the classic thing is that in Microsoft Word, the system crashes and it gives you a few previous versions to choose you to want to use. So in a stateful protocol, this kind of thing happens. So no need for client server to track state of multi-step exchange. All HTTP requests are independent of each other. No need for client server to recover from a partially completed but never completely completed transaction. So this is what happens when you have stateless communication. But in a stateful protocol, both parties will have the same state or data, okay? So websites and client browser use cookies to maintain some state between transactions. There are 4 components. Cookie header line of the HTTP response message, cookie header line index HTTP request message, cookie file kept on user's host managed by user's browser, backend database at website. Okay, so these 2 are headers in the HTTP, and these 2 are file, or actually this is a database entry, but in your computer you have a file for that web page. So example is as follows. Susan uses browser on laptop, visits specific e-commerce site for the first time. When initial HTTP request arrives at site creates a unique ID, which is also known as cookie. And in Turkish, we call it çerez, which I don't know why. Entry in backend database for ID. So they create the ID and write it to their database, saying that this user will be now referred to with this unique ID. So it is generally a very large integer, okay? Randomly created most of the time. So subsequent HTTP request from Susan to this site will contain cookie ID value, allowing site to identify Susan. So this way, if you use the same ID in different devices, they will always know who you are. Actually, this happens when you create an account. So here's an example. Assume that this client in their browser has a cookie for eBay, but doesn't have anything for Amazon. So when you visit all of these web pages, the folder, storing all of these cookies, becomes enormous. And in the past, when we have small hard drives, it will be nice to delete all of these cookies. But nowadays, people even don't know that there is a cookie file, okay? So this person hasn't visited Amazon before, so okay, here they create the usual HTTP request message. Now Amazon sees this client for the first time and realize that their HTTP request does not contain a cookie header. So for this reason, Amazon randomly creates an ID, in this case something small like 1678, and writes this to its database to record all of these actions of this ID for this user. And when they respond back, in their response, they have a specific header saying set cookie to this number. So now the browser creates a cookie for Amazon with that ID. So now this is a file on your computer. And so after this point on, you always do the HTTP communication with a header including cookie with this number, okay? So 1 week later, if you visit Amazon again, you will again request the HTTP, but with this time, instead compared to your initial request, now your request has a cookie header. Now Amazon knows who you are because they get this number, go to database and know who you are and respond accordingly. Because in the past week, maybe you bought something or visited some items but didn't buy them. They know it, so now they will show you a web page depending on your previous actions. So there's a state. This is the idea. So what cookies can be used for? Authorization, shopping carts, recommendations, user states, session state when you are using web email like Gmail and so on. Challenges are how to keep state at protocol endpoints, maintain state as sender receiver over multiple transactions. In messages, cookies in HTTP messages carry state. But now let's look at the privacy part, which is more important to us because we are dealing with security and privacy. Cookies permit sites to learn a lot about you on their site. Third-party persistent cookies, tracking cookies, allow common identity cookie value to be tracked across multiple websites. So I think here's an example for that. So you're going to visit newyorktimes.com and there will be, maybe advertisement there, okay? So what happens is as follows. You connect the New York Times with the classic HTTP GET method and they reply back, okay? This is the third step. At the fourth step, now you visit because the web page here has an object for an advertisement, and that advertisement is, provided by this web page. So you request the ad, and they give it to you. Okay. Now, New York Times page with embedded ads displayed, right? This is what happens. But the thing is that when you visited New York Times, they created a cookie for you. And for instance, you visited sports section of New York Times. Now they know that you're interested in sports. So now you have the cookies, okay? Now when you require an advertisement from the refer New York Times sports, they also add it as a new cookie here, okay? Reply back to you. Now you created a cookie for this web page. But the thing is, you actually visited New York Times, not this web page, right? But now you have a cookie for that advertisement web page. So the third-party cookie from website you did not choose to visit. So here is a very obvious concern, as you can imagine, because you didn't want to visit that web page in the first place. And actually, nobody knows that they visited there because they thought that they are simply visiting New York Times. Okay, so there's another web page here. For instance, they will use this advertisements companies advertisements here, saks.com. So now you visit them. Saks actually refers to this web page, and they already know who you are, and they will provide the advertisement accordingly. So edX tracks my web browsing oversight with edX ads can return targeted ads based on browsing history. So whenever I visit a web page that has advertisement with this company, they will know all of the web pages I visit. So think about this way, almost every web page uses Google advertisements, right? Google AdSense. So Google knows almost everybody's every action. So if you did something on the internet, most probably Google knows it. That is the idea. Yeah, one day later you can do the same thing. Now you visited arts section of New York Times. They also added that. Now they know that you are interested in art, but they also know that you visited web page and returned ad for Saks and so on and so forth. So cookies can be used to track user behavior on a given website, first-party cookies. But if there are third-party cookies like the one I showed as the advertisement, so first-party cookies like, you visit Amazon and Amazon creates a cookie. But if there's an advertisement there, that advertisement company is the third-party cookie. Just imagine Turkish newspaper web pages. It is like a billboard. You visit the web page and there are almost hundreds of advertisements around. And the bad thing is that sometimes those advertisements contain malware. You have a proper antivirus software, sometimes they warn you, saying that, this try to inject something. So there's both security and privacy concerns when you have third-party cookies, because you visit a newspaper web page, but simultaneously, actually, you visit like 30 web pages, which you don't know. So track user behavior across multiple web pages because those third-party cookies are everywhere without user ever choosing to visit tracker site. Tracking may be invisible to user. Rather than displayed ad triggering HTTP GET to tracker could be an invisible link, right? Because you never just, look at all of the source code of the HTML or so on. Right? You never know. Third-party tracking via cookies, disabled by default in Firefox and Safari browsers, to be disabled in Chrome browsers in 2023. But actually, it wouldn't be enough, So here's a example what the book says. So talking about GDPR and cookies. So natural persons may be associated with online. This is an excerpt from GDPR. Natural persons may be associated with online identifiers such as Internet Protocol addresses, cookie identifiers, or other identifiers. So they say that as long as you are anonymously represented with an identifier, it is okay with GDPR. But this may leave traces which, in particular when combined with unique identifiers and other information received by the servers, may be used to create profiles of the natural persons and identify them. So at that point, you have to abide the laws created by GDPR. So a basic example is that just imagine all of these examples I gave you. I visit New York Times, so the cookies are created and so on. So I'm identified with an ID, a cookie ID. So that advertisement web page knows all of my actions, but they don't know who I am, right? But if I log into my Facebook account, and if the advertisements are also uses third-party cookies there, they know that my name is Cihangir Tezcan, right? Because I connected to my Facebook account, my Twitter, Instagram, whatever. So representing them with a unique identifier in the future will turn into learn them who you are. And actually, this is why all of these services are free. Think about WhatsApp, Facebook, Instagram. You're not paying any money to them because they are selling your data to companies, and those companies can use these identifiers to determine who you are. So how can we avoid them? So there's a picture I want to show you. But when cookies can identify an individual, as I mentioned, cookies are considered personal data, subject to GDPR personal data regulations. In Turkey, we have KVKK for that. So for this reason, they always want to have your consent. Okay, this is why you have to, press I accept button. So here's an example. So here's a cookie here, as you can see. So here, this is the good version. Okay, the example the book shows you, but it is like this. This site uses cookies and gives you control over what you want to activate. Here are three options: okay, accept all, deny all cookies, personalize. So when you click personalize, they will give you some options to which cookies you want to prefer. But the problem is that this is the good version. In the real world, actually what happens is that this cookie bar actually covers almost the whole screen. So you cannot see the web page without making any choice. And accept all button is all green and big. And there is other button which actually when you click it gives you a lot of options and a lot of steps, and at some point you say that okay, I don't want to deal with this, just accept all of these cookies. And this is also against, by the way, GDPR. They have to be neutral like this in this example. So I'm sure that in your life you experience many different cookies, web pages. So there's a nice game here. I want you to go and play it, terms and conditions games, and check your evasion skills. So they will give you many different questions, cookie questions. So you will try to choose the correct answer. So in the break, I will show you how it is done. But again, it is still not okay here. I mean, what if they show me this option? If I don't click anything, or if I click deny all cookies, do you think that they still record all of your actions or not? Because in the past, I always claimed that, okay, I personally observed a few stuff, even if I, denied the cookies or didn't click anything, I felt like that they gathered my information. So I always claimed this, but I didn't have any scientific proof. So thanks to some people in Leuven and Belgium and Holland, Netherlands, they actually wrote a paper. This is a Unix 2022 paper. Leaky forms, a study of email and password exfiltration before form submission by Asuman Şenol, which was my actual thesis student here, and Güneş Acar was a Turkish person, and Matthias Humbert and Borgeseus. So in this paper, let me briefly explain what they did. In order to find out whether access to online forms is misused by online trackers, they present a measurement of email and password collection that occurs before the form submission on the top 100,000 websites. So they visited the top 100,000 websites of the internet, and they filled the form without pressing the send button and wanted to check if their data still leaked. And they observed that email addresses are exfiltrated to tracking, marketing, and analytics domains before for submission and without giving consent on around 2,000 web pages in European Union and around 3,000 web pages in United States. So, this is a huge percentage compared to this number. So this is why I hate cookies. You cannot avoid it. So the proper thing is that go to your browser and disable cookies. So this way nobody can track you, but this also means that you cannot visit any web page. It will not show properly. They will say that you have to enable cookies to visit this web page. Okay. Of course, one solution is that stop using web. Yeah, that might be an option. Okay. So this is why, I don't like cookies, and actually they should be banned. There should be some legal consequences for using cookies, which GDPR tried to solve, but all it did now, I mean, even before the GDPR, what we have is now an annoying box telling us to, accept all cookies. All right, so I will finish this part with web caches because it speeds up our web experience, but it should be considered in terms of Wireshark processes or in security cases. So goal is to satisfy client requests without involving origin server. So this is because there are a lot of requests. Maybe, for instance, think about it in this way: 2 people in the campus want to visit the same web page. So requesting the same thing twice, why don't you catch it? That is the idea. So instead of in the campus, for instance, in our university, assume that we have a web cache. So user configures browser to point to a local web cache. Browser sends all HTTP requests to cache. So here, if checks if object in the cache. So if it is there, it returns the response without going to origin servers. But if it is not there, it visits the origin server, gets the response, catches it, and gives it to the client. So if another client also wants the same object, the cache will have it and provide it. So this is the picture for that. So web cache acts as both client and server. Server for original requesting client, client to origin server. Server tells cache about objects allowable caching in response header, like this, no cache, or you can provide how many seconds it will be stored in the cache, because keeping a cache for a few days might not be a good idea, because most of the time web pages are updated regularly. Yeah, by caching, reduce response time for client requests, caches closer to the client, because it is our same institute, right? We can instantly get the object. Reduce traffic on an institution's access link. This is also a good thing. Internet is dense with caches, enables poor content providers to more effectively deliver content. So this is the good thing. So here's an example. Scenario is here. So your outlink from your campus to public internet is slow, like 1.54 megabits. But inside the institution, you have fast communication like 1 gigabits per second local area network. So assume that RTT from institution to router is 2 seconds. Web object size is 100 kilobits. Average request rate from browser to origin server 15 per second. So average data rate to browsers is 1.50 megabits per second. So at this scenario, the access link here utilization is almost 97%, which is very close to 1. So recall our previous lectures when I said that it is close to 1 request and response timing. This means that there will be huge delay at this router. So anything larger than 0.8 would be a problem. So your aim would be to reduce this, because here we haven't gone into the mathematics much here, but in every 15 seconds there's a request to download this kind of object. So this is why there's a queue occurring here. But the good thing is that this causes a problem. But at the local area site, the utilization is really low, because you're not transferring anything at the speed is large compared to this. So idea is to instead of wait for minutes, put a web cache here. I mean, of course, one solution might be increasing this speed, but it will be costly, right? So instead of 1.5, you can increase it to 154 megabits per second, but you have to pay money to have the infrastructure and so on. You can get rid of this. But cheaper solution is that just put a desktop PC here, call it a local web cache. So instead of sending all of your requests to outside, first send it to cache. If something is in the cache, reply it back. If it is not, then go to the public internet. And now, if the cache hit rate is 40%, this means that 10 out of 4 of your requests will be in the cache, so you don't have to go outside for that. So if you do the calculations, this means that the average delay will be very small, like 1.2 seconds. In the previous example, it were minutes, but now, so instead of paying money and increasing this access link capacity throughput, now you just use an old PC to have faster internet. So this is why we use caches, and this also happens in the browser. So browser caching uses conditional get. Don't send object if browser has up-to-date cache version, no object transmission delay or use of network resources. Client specify date of browser cache copy in HTTP request. So you write as if modified since and write your date of the time you cached it. So when instead of downloading the object again, you just ask the original server if it is modified since this date. And if the answer is no, then the browser provides you the cache version. If they say yes, you download it. Yeah. So server response contains no object if browser cache copy is up to date. So it returns 3 or 4 not modified. So you just check if it is modified since this date, and if it is not, you don't need to download the object because you already cached it. But if it is modified, they send you the data. Now you cache this one. This is important because sometimes browsers make a mistake at this point, because I update a web page, but students tell me that they still don't see the update. I ask them to press F5 button to refresh the web page, and at that instant, the browser, instead of showing you the cache version, really goes to the web page and comes back with the real answer. This might be due to a server misconfiguration. Okay, so if you don't see a web page properly, just press the F5 button in your browser. Of course, if you're on the PC, and you will realize that they will go and obtain the correct version. Okay, let's talk about HTTP version 2 here. Key goal is to decrease delay in multi-object HTTP requests. So I mentioned that if you want to request 10 objects, you have to create either in the non-persistent one, create 10 TCP connections, or in the other ways you request them in a serial way. But the thing is that there is something called head of line blocking hole. So let's read it and let me explain it in pictures. So HTTP 1.1 introduced multiple pipeline gets over single TCP connection. Server responds in order, first come first serve scheduling, to get requests. So this means that if you visit a web page and assume that at the top there is a video and then 10 small JPEG images. So you request all of them, but first you request the video file, and it is large. So you have to wait for that to be downloaded, then you will obtain the JPEG images. This is why, if you're older enough, you will notice that JPEG images slowly loading on web pages from top to bottom. That is the reason, because they work as first come first served. Okay, so with this FCFS scheduling, small object may have to wait for transmission behind large objects. This is called head of line blocking. Loss recovery, retransmitting lost TCP segments stalls object transmission. So these are the problems of HTTP 1.1. HTTP 2 tries to solve this as follows: increase flexibility at server in sending objects to client. And here method status code most header fields unchanged from HTTP 1.1. Transmission order of requested objects based on client specified object priority, not necessarily FCFS. Push unrequested objects to client. This is the good thing. For instance, let's remember our previous example. You request an HTML file and the server sends you the HTML file, right? But server already knows that there are 10 JPEG images in it and they know that you will request them, right? So instead of waiting for you to request them, they push all of the JPEG images also. This is the good thing with HTTP, to the push unrequested objects to the client. So you request the HTML file, they send you the HTML, but also pushed the unrequested JPEG images. But more importantly, they can now divide objects into frames, schedule frames to mitigate hole blocking. So here the idea is as follows. In the 1.1, you send requests of 4 objects, but you requested object 1 first, and the object 1 is really large, right? So you wait for that to be transmitted, then the smaller objects. But if you divide it into frames, like this, so server sends data frame by frame. So you requested 4 objects, and server sends the first frame of all of these 4 objects. But the good thing is that these images were small, so they're only 1 frame. But now the larger object divided into frames, so they send you already the first frame. Now, in the remaining parts, they send you the remaining frames. So this is why actually web is faster than before, because you don't feel it, but there is this kind of updates happening in the background. So HTTP2 over single TCP connection means recovery from packet loss still stalls all object transmissions as in HTTP 1.1. Browsers have incentive to open multiple parallel TCP connections to reduce stalling, increase overall throughput. No security over vanilla TCP connection. Still, again, these are, in the HTTP 3, there will be more updates, but still it will not provide you any security. We have to overcome that problem with TLS and so on. So HTTP 3 adds security per object error and congestion control, more pipelining over UDP. Okay, so HTTP 3 will provide more properties, but it will not, throw out TLS, okay, in terms of security. So we will talk about it more in the transport layer.